way. Just wait there. So Jim, please, then if you have questions, please do it in the microphone. So raise your hand and we'll give you the microphone.
Okay, I do encourage questions. Questions keep us awake. I have a hard time staying awake. It's a problem for me. And if there are questions, even if I know the answer, then I feel, oh, good. And if I don't know the answer, I'm very glad somebody else asked the question. So I think this is important. One thing, many of you will come to the exercise session of Pier Francesco. I'm terrible with names. Ubani, I think. Don't quote me. And I have exercises on Thursday. But my exercises are going to be not things I write on the board. They're things I hope you will read beforehand. And you have to find them. And 2 people found them so far, and I thought I would tell you where they are. So here is the class, the website. And under videos and files, you will find all of our presentations, except for the ones that don't have files. So, and under my first lecture, the abstract, okay? You click on that. There's no abstract, but there are exercises. Life is short. We have good technical people here, and I gave them in a rush, and they put it here. Okay, so I'm not complaining. I'm just helping. So here. And so this is what I want you to do. Before you come on Thursday, I've gotten 3 choices. So we will have one group over here, one group here, one group there. And Stephen, who's done this before, and I will run around trying to help people. And the 3 choices depend upon whether you have a computer and like it and know either Mathematica or Python. That will be one group. Next group will be if you don't have a computer or really want to understand the renormalization group and don't feel like building avalanches. Maybe that'll be in the middle or something. And then there's a 3rd group that will be wanting to listen to crackling noise and chaos and look at pictures, which I think is perhaps the most fun. And you have to decide what you want to do before you come. Otherwise, you will spend all our time reading, trying to figure out which lecture thing you want to do. If you have the first one, I want you to make sure that you can get to the audio files. And that's the website. And if you get to the PDF, you should be able to click on it. It'll take you there. And then you scroll down to the exercise, which you will find 12.14 and 2 other exercises. So the noisy one has 3 different exercises. Second one, I want you to do part A. Part A will get you thinking, will get you, it won't take for very long, but I want you to do it before you come. And then the 3rd one, for those people who are experts in renormalization group and feel like drawing cool pictures of avalanches in time and histograms of sizes and things, that will be, that's the same website, a different exercise number. It's the last one in this 17-page output. and I'd like you to read it a little bit and download the hints files. So I find I can get you to do very sophisticated things if I give you hints as to how to do it on the computer. And okay, everyone good? All right. Today, I tell you, no, I'm not saving, I'm running. Good. Today I will give you examples of universal scaling functions for different avalanche problems. And first, it's good to have examples in your head. Second, all but one of the examples will try to introduce a feature that shows up in the calculation I will do Friday. Okay? So there's all kinds of, so there's a crossover scaling function, and there's a correction to scaling, and there's a dangerous irrelevant variable. And I will tell you all about these things today. And so that when you see them again, it won't be, oh no, all more gibberish I don't understand, but rather, oh, there's another dangerous irrelevant variable. That's cool. All right? All right? So, first of all, what's an avalanche? We talk about avalanches like everyone, of course, knows what an avalanche is, and they say earthquakes, and you say, okay, that's an avalanche. But an avalanche is a jump between two metastable states in a disordered system. That's the way we think of it. Okay, that's the way we use the language. It starts from some weak spot. And then that weak spot transforms in some way, and then it increases or decreases the stress around it, triggering other weak spots. An avalanche, if you're in a region where the avalanches get big, they often look fractal in time and space. And you saw a little bit of that last time. They come in all sizes. You get scale invariant avalanches near the onset of flow or failure, like in my model, when the field hit a certain value, they got bigger and bigger and bigger, and then blam, an infinite one. But also, if you have a granular material, real sand piles don't work this way. But theoretical sand piles and certain very carefully arranged rice piles, when you start pouring them, they'll have, at a critical angle, they will start flowing, and near the critical angle, it'll look avalanche-y, and systems of all scales. There are other cases where it's the same kind of, you tipping it until it starts flowing, but it's self-organized. So you take this pile of rice and you tip it and it starts flowing, and then you adjust it until you get just a very slight trickle on average. If the average velocity is how you control it, you'll automatically be at the critical slope. And then sometimes you get what's called generic scale invariance in general, where a whole phase will have avalanches of all scales. And one of these examples is in plastic flow in metals or in amorphous materials, where you start shearing, one site will typically slip, and it will trigger other sites, and the interactions are so long range that that you would trigger an infinite number of sites, except that you get a hole in the density of states, so there aren't very many weak spots, and then da-da-da, you get avalanches of all scales long before you hit the point where it starts just flowing. All right? Yeah?
Jim, can you understand what you meant by the self-organized approach?
Self-organized was a big, fancy name for you take a system that has a critical point, and then you arrange for it automatically to sit near its critical point. One example was earthquakes and rice piles. Rice pile, you tip it, and you let it, and you hold it at an angle where it just barely trickles off the edge. Now, of course, it'll trickle off, whoosh, and then very quiet, and whoosh, and very quiet. There are avalanches of all scales. But if you hold it there, you'll get avalanches of all scales because the velocity, the average velocity grows continuously as you cross this threshold for the rice. Same thing is true of earthquakes. At least we don't understand earthquakes completely, but we know that the continents move very slowly, and so you know the average velocity due to the earthquakes is a few centimeters a year, and that means that you're extremely close to the threshold force for flow of the earthquake fault. Another example, which is kind of trivial, is if you have a material and its properties are varying smoothly with position. You have an inhomogeneous material, a bad sample. And then somewhere along there, it'll go through a critical point. And you automatically, when you measure the properties, it'll look like power laws and scaling. Okay. Oh, mine doesn't work any better than... Okay. Simple model. I like it. Yes?
There is some parallel between avalanches and
Intermittency and turbulence. Intermittency and turbulence is, for those of you who don't know, there's an old theory of turbulence that explains sort of the cascade of energy to shorter and shorter length scales, which predicted things that weren't quite as dramatic as real turbulence. And when you correct that theory, you find that there's a large concentration of velocities in small regions. So if you're in this situation where you've got white water in rapids, or turn up the tap until it goes whoosh, there are eddies, and there are eddies inside eddies, and there are eddies inside eddies and eddies. And those eddies will leave large regions sort of not moving, and a few regions that are really twisting and shearing strongly. And this intermittency has its own scaling and looks like a renormalization group should apply, and nobody's figured that out. Excuse me. Nobody until recently has figured it out. There's a non-perturbative renormalization group calculation that looks very interesting, and I've always found that encouraging, that maybe we're going to be close to understanding things. Most of this is not necessary to build airplanes. There's an effective engineering theory with eddy viscosities, but our fundamental understanding of turbulence ought to be our job and hasn't been solved. Okay. Or maybe has only recently been solved. And then what to do with earthquakes, I don't know. Good question, though. Okay, so you all have read in the paper about pandemics. You have infected people, and you have not yet infected people, and each sick person infects this magic R0 number of other people, and there's a critical point where R0 is equal to 1. If you're bigger than 1, then obviously you keep getting more and more people sick. If you're less than 1, it dies away, goes extinct, we'd like to think. Okay. This is very similar to the model of the mean field random field Ising model. Mean field means every spin talks to every other one. The spins start at -1, external field H triggers the weakest spin, and this is a two-dimensional example of an avalanche. 13 was the weakest spin, it flipped over. Then it has 4 neighbors, this is a nearest neighbor Ising model on a square lattice. 3 of its neighbors flipped over. And then after that, I actually did a little tiny simulation to do this. Then these 5 flipped over. And then after that, these 4 flipped over, and then it stopped. All right? Yep.
The flipping rule now is it probabilistic or?
It's dependent. Okay, so this guy flipped over because it had the biggest random field. So it was the first where the external field plus the random field was bigger than 4 times the coupling to the neighbors. Then this guy flipped over because the external field plus 2 times the coupling to the neighbors was positive, because it has 1 neighbor down and 1 neighbor down and 3 neighbors up. 1 neighbor up and 3 neighbors down. 1 neighbor up and 3 neighbors down. And so there's net 2. And these 3 flipped. And then this guy, then these 3 flipped for the same reason. And then this red guy suddenly has 3 neighbors pushing them over. And so even though it resisted after the first one, it succumbed after 3. Good? Very tangible picture in your head. Very tangible connection to a pandemic if you can only infect your neighbors. If you don't infect your neighbors, you infect anyone, then it becomes the same as your typical newspaper model. Okay? And you can look at the size distribution of the epidemics. If your R0, if R is close to R0, you're going to have some pretty big epidemics before they die away. And it turns out the universal exponents, tau is 3/2, sigma is 1/2, and you get a scaling form, s to the minus tau, p of s to the sigma r. Now, I'm telling you this not because that's what I want to spend all my time thinking about, but you've seen the avalanche size distribution a lot before. This is the avalanche size distribution in mean field. And this universal scaling function, because it's mean field, we can just solve for it. And it's given by e to the minus whatever the argument is squared divided by 2. Everyone happy? Okay. So this will be a power law cut off with an exponential, which is the square of s to the 1/2, so it'll be exponential in s. And this is that invariant scaling combination I kept telling you about, x, s to the sigma r, right? Everyone happy? Everyone feels now like this kind of formula is your friend rather than another random, mysterious thing that, okay. That's what I'm hoping.
Just a question, S is the size of the avalanche that you're...
S is the size of the epidemic.
Okay.
Yes, or the avalanche for the random field Ising model. Yes. Number of sites.
In this case, the size will be represented by what? The number of individuals.
The number of people sick, the number of squares flipped over. Yep. Very, very tangible. Okay. What I'm going to tell you about is another story. Same model, same mean field, with an experiment. So this black line was measured by Bone, Sommer, Duran, when Gianfranco Duran was on sabbatical in Brazil at Rio de Janeiro. I don't know whether you're all rivals of Rio de Janeiro. How many people are from Rio de Janeiro? Anybody? All right. So this is a really tough experiment, not because it's hard to find avalanches in magnetic systems, but because we had to do it in a very thin film to get rid of other problems. It's very noisy. I'm just giving you some context. It's very noisy, so normally what people would do was say, well, we'll figure out where it stops. There's a little bit of noise. We can't tell it's actually stopped. So we'll say it stops when it crosses some dotted line. But the noise is so big, you'd have to make the dotted line way up here. And so this thing that's obviously one avalanche to you, it would look like 10 avalanches. So Stefanos Papanikolaou, the first author, spent a huge amount of time figuring out how to do optimal Wiener filtering. You don't have to know what that is. And he got this red line that said this is probably what the avalanche looked like. And so we decided it stopped here, it started here and ended there. You could argue it might have stopped a little earlier, but roughly speaking, we think that's noise. Best guess. And then this green thing, which is what I'm going to spend my time a little bit talking about, is the average avalanche shape. So we took all the avalanches with this duration. This was an experiment that collected a lot of data, and we averaged them. Yeah?
What is avalanche temporal shape? What is this function?
This green thing is the average shape as a function of time, average temporal shape.
But what is the, sorry, I'm not expert in this field.
Yes?
What is the shape of an avalanche?
The shape is this black curve, or the red curve, which is our best guess as to what actually happened without the noise. That's the shape. Then the average shape is you take all avalanches the same duration, the same time between the beginning and end, and you average them and you get this green curve. And then here are a bunch of different avalanche shapes, all fixed so that their peak is at 1, just to make the plot look nice. Obviously, if the duration is very long, the avalanche typically goes much higher. And if the duration is very short, then it would be very small, so we just rescale it. Now, yeah.
What's the blue dotted line?
That was the old method of trying to figure out when the avalanche began and ended. And I was,
Subtraction, then you just look at
yeah. And for normal experiments, That works well, and all the experimentalists know about it, and I was just bragging about Stefanos's hard work in figuring out a much more clever way of telling when the avalanches started and ended, which we recommend to experimentalists, but you don't really need it unless you're doing a hard experiment. Okay, so now, universal scaling functions. What does this have to do with it? Well, the universal scaling function for the average avalanche shape, you can argue, has a ratio power laws T over the duration. So this is time, and the duration is the beginning and end point for that avalanche. And only the power law ratio is 1-to-1. You don't have any difference in the scaling of two things that with units of time. But then there's this extra parameter, and I have to explain that a little bit, that in most of these problems, you have a cutoff in the avalanche size distribution. Here it's caused by something called the demagnetizing field. You don't need to know what that is. But there's some reason that the very big avalanches get cut off. What's happening is for the very long avalanches, the long avalanches don't keep going up and up and up and up. They're just short avalanches that happen not to die. Normally, they would be expected to die after a certain amount of time, but they're lucky. They keep going. They're luckier. They keep going more. And so they end up not getting as high, but they get sort of flat on top. And this is the experiment. This experiment is in a regime where we think mean field theory is appropriate because there are long-range forces due to the magnetic fields. And this is the theoretical calculation. You can really solve this problem, and you can get a beautiful agreement with this experiment. Is this okay? Yes?
How can I interpret this kind of signal from a magnetic system? For example, when I see a similar signal for a crackling noise, for example, I can understand that this refers to the intensity of the noise as a function of time.
Yeah.
But in a magnetic system,
you measure the intensity of the magnetic field changes in the material. In fact, there's a great experiment that I sometimes show off. You take a coil of wire, you hook it up to a microphone, no battery involved, and you take a big iron nail and put it through the wire, and then you bring a magnet up. And the magnet will cause little domains to reorient in the iron nail, and those rearrangements emit dm, dt, pulses, and you listen, it sounds like crackling noise. Yep. But it's only crackling noise because you have a coil hooked up to a microphone. Otherwise, it's magnetic noise. It's called Barkhausen noise. Good questions. Thank you for asking questions. I've got stuff at the end of this lecture I don't need to tell you, so I'm happy. So I keep trying to hit the buttons, but theirs doesn't work and mine doesn't work, and it's probably my laptop, which, anyway. You remember, okay, I'm now first topic. See the asterisk up there? That's saying this is something that's going to come up again on Friday. These are what we call singular corrections to scaling. I haven't told you what that means. I'm about to tell you. So you remember the avalanche size distribution from the random field Leslie model in 3 dimensions? And you remember that when R was far away, when I'm not near the critical point, it didn't work so well. It had a systematic deviation, right? And I said, well, you expect it to work near the critical point. Over here, I'm going to tell you about this in a moment. Here, when I get very big systems, I get this orange curve. But when I have smaller systems that are a lot easier to simulate, I get these curves that systematically deviate in the other direction. They grow as you get to bigger and bigger systems. Now, what we can extrapolate in our heads to get this black curve, and here we can extrapolate in our heads to get, if you can see very carefully, there's a dotted line almost sitting on top of the orange curve. But what's causing this thing? What's causing the deviation? Can we use our theory to make sense of that deviation? To make a universal prediction for the corrections to the renormalization group prediction? Okay? These are called subdominant because they go away when you get closer and closer to the critical point compared to the main effect. Okay, so this is where every day I forget something, but I have it here. It's my notes. As you get older, some things go away. I never was very good at algebra on the board, but I think it's important to occasionally make use and exercise my brain. Yes. So, singular correction to scaling. Oh, geez. It'll be easier to understand me without my mask on. And compared to eating lunch, it's a trivial amount of extra danger. Singular corrections to scaling. And it says, irrelevant variables matter too. All right? So you remember the renormalization group flow diagram I drew yesterday, where these were big avalanche, and these were small, and this was blue and irrelevant, and this was green, or I think, or maybe red and relevant. You remember that? How many of you remember? Exercise your arm, keep you awake. Okay? So now I'm going to try to say that these irrelevant directions produce these corrections to scaling I was talking about. So we're going to have RG flow equations. dx dl is ax. dy dl is by. dz dl equals, any guesses? cz. And then du dl, this is our irrelevant guy, is going to be minus d times u. This looks wrong, but this is a different kind of d than that, okay? Then we have invariant scaling combinations. I wish I had a nice name for them. I think they're really important, but I can't think of one that hasn't been stolen for something else. They're not the scaling variables. That means something to various different groups. They're not that, but anyway, these are the invariant scaling combinations. Capital Y is y over x to the beta delta, which is y x to the minus b over a. You remember that from my bad algebra yesterday. And u, capital U, is u x to the omega, which is u x to the d over a. You won't be surprised. There is a new universal critical exponent little w. Or sorry, omega. We're calling that omega. Okay? It's universal. It's found, it's a property of S star that flows near S star. Any system flowing to S star will have the same omega. It's just an irrelevant thing because as x gets close to its critical point, capital U gets smaller and smaller. Good? So there's a universal scaling function. This is z of x, y, and u, which is what you would measure. I'd like to, every once in a while, remind people, this side is what you measure. This thing is equal to x to the beta times universal scaling function of capital Y and capital U, which is little x to the beta, the same function of y over x to the beta delta, just as you had before, and u x to the omega. Not a surprise, right? You believe me. I don't have to check to make sure that I can differentiate. Okay, now here's the point. Because U becomes small as little x goes to 0, right? Capital U becomes small as x goes to 0 if curly z of capital Y and capital U is differentiable as capital U goes to 0, then I know how the universal corrections to scaling will look like. Little z of x, y, and u will look like x to the beta capital Z of y and 0, I'm Taylor expanding about 0, u, plus x to the beta times the derivative of z with respect to u, times u, times the derivative of z with respect to the second argument, which Mathematica writes with a bracket 0, 1, and I'll do that too, of capital Y and 0. This is the correction to scaling. Capital U is going to 0. And when I go back to the original physical variables, so this is x to the beta z of y over x to the beta delta is 0. This is the dominant part. And then this becomes x to the beta plus omega, so it goes to 0 faster, subdominant. Times little u times z 0, 1 of y and 0. So I evaluate the first derivative times it times the derivative of the function evaluated at 0. So this is a non-universal amplitude, and this is a new function which is universal, and it gives the correction. Good? So now I'm going to give an example. This is this fractional problem that I showed you the picture of before. Yeah?
How directly I can consider zeta as a differentiable function at u equals to 0? Because I'm not reaching some, I don't know, some fixed point, something like that.
So, you're asking me, can I always trust that z is differentiable at 0? And you notice I said if with 2 underlines. You cannot always trust that. You should normally expect it, but you should verify. Okay? To quote a famous Republican before they really went crazy. Sorry. Okay. So this is the model that I would like to show off singular correction to scaling. This is what we call singular correction to scaling, these subdominant, smaller, but still important if you really want to describe experiments, not just right at the critical point. This is a model for what we call quasi-brittle fracture. Take a piece of glass, hit it with a hammer, you will get one, hit it with a small hammer, not too hard, you'll get one crack in your windshield that starts with a little fracture and then goes, and goes all the way through. If you start with a piece of malleable metal and you start breaking it, it will break lots of goopy things going on microscopically. But if you take a seashell or a bone and you try to break it, lots of little bits will break long before the big one. Okay? that you will, and this is a simulation of a model for fracture, which is a fuse network. So you have a bunch of fuses, and instead of putting stress and springs, you put current and bonds. Fuses are the things you put in your house to keep it from burning down when you plug in something that's too big and it heats the wires up and otherwise would burn down your house. It just put too much current, it blows. And this is a network of fuses. And this is something that would look a little bit like a glass fracture, except that before that happened, all these other things broke. And seashells, this turns out to make seashells much harder to break. You say, yeah, it's got all these weak spots in it. But the weak spots keep the crack from growing very much, because every time the crack tries to move, it has to break all these other things, and that consumes more energy. It's a typical thing in fracture. All the things that you think will make it harder makes it more brittle and easier to break. So glass is really hard. Much harder than steel. If you take a piece of steel and you scratch it with a sharp piece of glass, the glass won't break, the steel will scratch. Well, glass will break, but anyway. You get power law distributions of these little black guys that look like a critical point. Okay, we were studying this. Ashwini Shekhawat and some students of Sethna's pair. I think Ashwini was the main person on this one. Beta will turn out to be disorder. Beta is, yeah. So some of these bonds are much stronger than others. And beta is a power law that I won't go into details, but as it gets bigger and bigger, when it gets smaller and smaller, you get, let me see, I will go to the next. Let me get to that. Beta is a measure of disorder. So, what's the problem with that? How come I know for sure that this is not a real critical point? So there were competing papers. Some people would say, oh, I've explained the power law distribution of precursors to fracture. Then other people would say, that's silly, you can't do that. There are no precursors to fracture in the thermodynamic limit. So this is where Leonardo da Vinci comes in. He did experiments that showed that the bigger the system, the weaker it is. Well, he didn't show that. He just said, you take a wire, you hang something on it, you put more weights in it until it breaks. Pardon?
You mean the weakest link model?
This is going to become the weakest link model in a moment, but Leonardo did not call it that. I'm still on Leonardo. Yes, but no, yeah, you're exactly right. So you put more weight and it breaks. Then you take one twice as long and it breaks earlier. What the point is that the wires in Leonardo's time were not perfect. Some of them were weaker than others, and so there was a whole distribution of fractures. Now that we have high technology, our wires are also breaking at different times. In fact, it's a fundamental truth that unless you're on the nanoscale, there's going to be flaws in anything you make. And things like fracture make perfect use the worst flaw you can find. And so a twice as long wire, there's going to be a weight at which the top half would break. There's going to be a weight at which the bottom half would break. Whichever one is weaker wins, which is the weakest link model. Same thing is true if you made thicker wires. except if I have twice the cross-section, you would think it would take twice the weight to break it. So it's the same stress. You've been hearing about stress. And so the stress threshold for a fracture goes down as you make it bigger. What's worse, you can argue for almost any model, including all the models that physicists come up with, that distribution of weakness extends to infinity. It extends to zero, infinite weakness, zero strength. Okay? That somewhere in a light year away, there's a little region a centimeter across where all the bonds are very weak. And that region, as soon as you put any stress, a light year away, it'll start this fracture. And if you wait long enough, at least a year, that fracture will pass by you and it's broken. Okay? And now what does that mean for precursors? Well, the stress needed to break a centimeter long crack is really small. And so you know that all those avalanches you thought you were going to have are going to be cut off at the point where the stress never gets very big. And so in the thermodynamic limit, there are no precursors. You'll get a few crackles along the path of the crack, but nothing far away. Okay, so how do we make an intelligent theory of something that doesn't happen in the one limit we understand as physicists, the biggest possible system? Oh, I'm going the wrong direction. That's the problem. Here we go. We call this finite size criticality. So our model, it's not a very sensible model. We tried to do better things with it, and we've come to the conclusion that it's a little crazy. But our model has a disorder, and this is why I was a little, I keep forgetting whether beta is the disorder or beta is the inverse disorder. And here I've written inverse disorder. I think it's inverse disorder. I think this is infinite. Beta equals 0 corresponds to infinite disorder. And at infinite disorder, everything breaks like a percolation problem. You remember percolation. You just break things in order of their strength. And the point is that every time you break something, it could break something far away because the currents or the stress is going to be redistributed and things far away will increase their currents or their stress. But if the disorder is huge, so that the stress at which this breaks is 100 times smaller than any other strength anywhere. And so the stress redistribution at that point is 100 times smaller than anything else. Nobody else is going to break. It'll just do it one at a time. There are no avalanches there. In percolation region, there's no avalanches. Everything is breaking one at a time. This is just the final crack that grew one at a time until it extended across the system, and then after that, there's no current anymore. Here is a large disorder, a small disorder where the first bond breaks, and pretty soon after a few precursors that are very small, not very big avalanches, you get one that breaks and it just rattles through the whole system. And there's a universal scaling function which gives you this power law that we see. It's a real power law, but it goes away when L goes to infinity. Okay, that as I change 1 over L, so yeah, there's something I forgot to mention, that size here looks like an irrelevant variable, just like U, but it's really 1 over size. That's the thing that's universal, the thing that's controlling things, and 1 over the, never mind. You didn't notice that minus sign here.
Simulating that exactly.
Say again?
Which system are you simulating that?
This is the 2-dimensional fuse network with a what we call a diamond lattice. It's a rotated square lattice, and you have a voltage across the vertical direction, and you blow fuses, and you distribute your strengths of the fuses with a power law distribution given by beta.
Disorder in the stress?
There's no disorder in the stress, there's disorder in the strength of the fuses. Some of the fuses will blow at small currents, and some of them take very large currents.
And how a large disorder how this distribution behaves? It's like Gaussian?
No, it's a power law. So
So it was a power law in the local disorder?
yes, the probability of having a fuse with strength X goes as X to a power beta, and so you can get a giant number of very weak stresses because beta is negative or something like that. Maybe it's minus beta. Yeah. Good. Now, singular corrections. Yeah.
You choose one of them as your parameter because f is analytic in it. You choose one variable, not L.
Oh. Finite size effects are relevant. L shrinks under coarse graining. L shrinks under coarse graining. You would think it would be irrelevant. But it's not. It's important. And the more you coarse grain, the more important it is. So it's 1 over L that we should have been calling our relevant variable all along.
I'm asking if there's a mathematical formulation which allows me to realize that.
If L is not infinity, then everything is analytic. But when L goes to infinity, it becomes non-analytic. So I'm not pretending that L is a 1 over L is the right way to think about analyticity near 0. It isn't. I'm not sure how to answer your question. I could imagine thinking about it deeply, but everyone else would get bored. Yeah. L could be set by the whole system size, or in a real material, often it's something like a grain size, yes.
Those boundaries, do they have a special meaning, like order transition?
Boundaries where?
Boundaries between the creation, avalanches, and percolation.
Oh, these dashed lines,
Yeah.
they're dashed because they're crossovers. That down here it looks kind of percolation-like, and in this region you get pretty nice power laws, but it's not like there are no avalanches bigger than one here, and it's not like there are no precursors here. They're not phase transitions. And that's one of the controversies. Some people had diagrams with real phase transitions, and that can't happen. But on the other hand, the people who said the fracture precursors can't happen aren't. I mean, this is a perfectly nice theory, very like the ones that had straight lines, except that we did a slightly different analysis. All right. So here's our data. And you say, this is not a very good scaling collapse. And I have to agree. It's hard doing these experiments. Ashwini wrote a wonderful code that everyone started using after they've been using one written by a professional programmer that ran in parallel on 100 processors, and he wrote one that ran on one processor. And it was so much easier to use, and really it was almost as fast. But you could only do statistics up to a size of 128. 128 is pretty small, especially these days. And so you couldn't do a scaling collapse. I mean, you could, but it would be wrong because you were pretty sure there were corrections to scaling. Yep.
Are you choosing the exponents to best collapse the data, or use
That's exactly my next point. Thank you for asking. So we use things that you don't normally know. We know everything about percolation. We know lots of the critical exponents without any fuss. We even know this correction to scaling, if I remember correctly. Okay, we know this exponent, we know this exponent. The only thing we don't know is anything having to do with disorder, because percolation doesn't even think about long-range forces. Okay? And so we could tell that this wasn't working, so we looked at it and said, must be a singular correction to scaling. We did exactly this. We made up a new function. So we made up a function that's this dashed line that it was our best guess for curly f. And then we made you can't do a scaling collapse to 3 variables, so this is the second moment of the distribution. This is a strategy, if you have a function of n variables, get rid of all but one by taking moments or something and collecting lots of statistics. But then we made up a second function that when you look at these lines through the data, that includes this new extra term where we fit this non-universal constant u, and we fit the function. Whew. There's my first example. Questions? How are I doing on time?
You have another half an hour.
Another half hour. I think we should spend a little time stretching before I plunge into the last half hour. Yeah.
But if you wouldn't have broken it up into x to the beta plus w and you this structure, this, you pull it out and it's just a reason. It's universal.
Yeah. Sorry, say again.
If you took only x to the beta out,
Yeah.
then this part would be universal.
Yeah. Well, I mean, the original function z of y and u is universal.
Yeah,
so the derivative is universal. Yeah. Mm-hmm.
Why is it useful to do the decomposition? Because this allows you to say...
Because you don't know what u is. One system will have u as 3, little u.
Yeah, but
one system will have u as 3, one system will have u as 0. If u is 0, there's no correction to scaling to this order. Else, mean field theory can get wrong, or whatever. Your theory will get it wrong, but it's not quite true. Your theory can also predict this, just can't predict this. Your experiment can deviate from your theory by the magnitude of this non-universal parameter. In the same way, it can deviate from your theory by having different x naughts and y naughts and z naughts. But here, the change involves another new irrational number, or in mean field theory, another new rational number.
Yeah, so just about the theorem we're predicting this, but this is given that you know what this variable u is and you can...
You don't need to know the variable u as long as it doesn't change in your experiment. This function will tell you the shape.
But did you fit this function, or did
Well,
do you have a...
You only need to fit it once. The next experiment has to have the same function.
Right.
This number, every time you do a new experiment, this can be different.
Yeah.
right?
And so when you compare the different system sizes, so does it also mean that U is different between them?
No, you presume that this is a property of the infinite system size. You might think there might be some kind of effective U as a function of size, but I think the right way to think about it is there's a single U, and then when size changes, that's all buried in curly Z.
Also coarse graining.
Pardon?
So we said U, you can coarse grain also at the same time. So when you change the system size, it should flow to 0.
No. Capital U is fixed under coarse graining. Right. And the point is that your experiment is crossing different contours of capital U as it goes to the critical point. And that's why this has a positive exponent. That's why this is subdominant. Okay, we should start again. This is not meant as a preview to lunch. This is meant as a, okay. Now I'm going to tell you about dangerous irrelevant variables. This is an answer to your question. What happens if it's not analytic? Okay? So suppose Z is singular in some way as U goes to 0. I was just found out yesterday, or yesterday night, from references that that Urbani gave me, that dangerous irrelevant variables are called something else by the high energy physicists. But this is, the condensed matter community calls them this. The Ising model for D bigger than 4, the magnetization M of T, H, and G, well, what is G? G is the quartic term in the double well that in mean field theory describes the phase transition. This is Landau theory. So you have a well that goes down and up, and the magnetization is where it hits the bottom of the well. And as your quadratic term goes to 0, that's like T going through 0, then you get when T goes to 0, you go from a single well to a double well. And Ken Wilson made his calculation that showed that everything was boring above 4 dimensions by noticing that G was irrelevant. So M of T, H, and G is T to the beta, curly M of capital H and capital G, where capital G is going to 0 as you go to the transition. And when you take this to 0 and T goes less than TC, you've got a quadratic potential that's going down. So the magnetization goes to infinity. That's not allowed. Okay? So there's something about curly M that when you take the second argument to 0, it goes to infinity to fix things. And if we had time and if I had prepared it, I could have told you how that worked. But it's a dangerous irrelevant variable. You need it there, even though it's going to 0, you can't do a Taylor series. The most important physical system is what's called a zero temperature fixed point. I'm going to tell you about glasses, even though we're only now beginning to understand them using techniques of Professor Urbani here. But this is almost surely correct for the random field Ising model. When I say almost surely, I'm not sure there's been a rigorous proof. But if your renormalization group flows make your temperature go to 0, the real temperature happens at finite temperature, glass transition. You cool it, it gets solid at some real temperature. But But as you coarse grain, the temperature looks less and less important until it's irrelevant formally in the renormalization group. So the competition is no longer between thermal and bond strength, it's between dirt and bond strength. That causes your experiments to die. Okay? You can't get to equilibrium. This caused horrible arguments in the early days. That the theorists had friendly arguments. I haven't told you this story already, have I? The theorists had kind of friendly arguments. Jeff Grinstein wrote papers on both sides. Is the random field Ising model, does it have a ferromagnetic ground state in 3 dimensions? And the supersymmetry people said, no, they can't. In fact, 3 dimensions gets mapped to 2 lower dimensions, and there's no phase transition in 1 dimension in the Ising model, so there can't be a phase transition in 3 dimensions. It's amazing, stupendous use of supersymmetry in ordinary life. So Jeff Grinstein wrote some papers on that, and he wrote some papers. He's a really friendly guy. Anyway, the theorists on the East Coast said there was no transition. On the West Coast said there was a transition. It falls out of equilibrium. Because if I have a temperature that's formally irrelevant, and I have a typical barrier height that flows to a fixed point, I will end up with a ratio of barrier heights over temperatures on long length scales, which goes to infinity, which means thermally crossing it takes an infinite amount of time. So you know, glasses get very viscous. They get very slow as you cool them. This is because of a 0 temperature fixed point. You can't throw it out of your theory if you want to know anything about dynamics. My third example is going to be jamming, that we find a dangerous irrelevant variable in the jamming transition, and I will tell you about that. Yes?
Excuse me. In the case of the Ising model for dimension greater than 4, you mean that the theory does not make sense, it's trivial?
The random field Ising model, the Ising model. The Ising model would be trivial but sick if you allowed G to go to 0.
In what sense?
In the sense that the magnetization below TC would be infinite.
So the theory is not defined.
But the theory is defined. It's a perfectly good theory. It's just the universal scaling function, curly M, compensates for the fact that the quartic term is going to 0 by making it curly M singular as G goes to 0 to keep the magnetization okay.
It could be a physical magnetization function in this case.
No. The 5-dimensional Ising model goes through a phase transition with a finite magnetization. Pardon?
The theory is not well defined. Appears to be not well defined.
I'm sorry?
The theory appears to be not well defined for D greater than 4.
It's not well defined.
What is not? What is not? The theory is, the true theory is well defined. The caricature, the bad approximation is by writing a scaling function like this. If you assume that curly M has a derivative and you can set G to 0, you get the wrong answer. But curly M you can compute perfectly well, and it doesn't cause trouble when G goes to 0. Okay? Good? Yeah.
Is it possible to introduce a new variable like U to avoid those problems?
What more do I need to say? I think I'm happy to take questions forever. Yes? Go ahead. Oh, by the way, he's not crazy, okay? There are problems where you take something through zero and the theory just doesn't make sense. Quantum electrodynamics. Quantum electrodynamics, you say? Quantum electrodynamics, they've got calculations that work to an amazing number of decimal places. They perturb in powers of the fine structure constant. The fine structure constant is 1 over 137. So each new order that they get, they're up to 8th order now, gives you another factor of 137 in accuracy. It's amazing. And then you're perturbing about alpha equals 0. Alpha is a fine structure constant, E squared over H bar C. If you make it negative, the theory is not defined. It doesn't make sense. You have a complex electric charge. And Dyson figured this out. And Dyson said, well, look, this theory is asymptotic. That is to say, you're perturbing about a point which doesn't make sense if you go past it. And that turns out to make the theory better. Stirling's formula that tells you n factorial, 0 radius of convergence. It makes no sense if you take it to, you're perturbing in 1 over the n for n factorial, and and as 1 over n goes to 0, you're perturbing about 0, and negative 1 over n has a dense set of poles every place. And Stirling's formula doesn't have a radius convergence. It's 0, but it works all the way from n equals infinity down to n equals 2 really well. Having a singular point that you're expanding about, as physicists, we can be pleased that it works better than having a radius of convergence because there's no natural scale, so that your theory, if it works at all, is going to work really well all the way to crazy points. So he has a lot of reason to suspect that if you have something that goes crazy when something goes to 0, maybe it's not defined. Yeah. So we were talking, and I was saying, no, it's okay here, it's okay. I was telling him it's not like quantum electrodynamics where it really does go crazy. Good. Other things. This is a fun conversation, but I will go. Oh, good. Thank you. Did you? He also had a question. Did you? You okay? Fine. Good.
It is possible to introduce a new correction to avoid problems like that. I mean, if we introduce the U, then we can introduce a new variable.
This G is the new variable for the irrelevant constant little g. That's what it was. And it went to 0 as t went to 0. And I changed notation from U to G because this is the standard notation. It's not quite the standard notation for the Ising model. Anyway, so this is the irrelevant variable, and we added it, and we can't take a Taylor series in it. Did you have a question, or are you just stretching? Okay, good. Okay. 10 more minutes. I can certainly do one slide in 10 minutes. And if I can't, I can always come back, right? So please ask questions. The other thing, another thing, maybe this is the last thing. Yes. I can do the next part at another time if we have time, but it's not crucial for the talk. The last thing we need to do to understand Fridays is crossover scaling. Okay, so sometimes you have a relevant variable that leads you to a new critical point. All right? So, as an example, here's some data on the roughness of a crack. I've tried to pick all problems where there's disordered elastic theory, and this is certainly one. The crack roughness is due to disorder, and it doesn't have to do with avalanches per se. We had crack avalanches before. This is other kinds of cracks that don't tend to produce avalanches all over the place. But the nice thing that you see here is you have two different power laws, right? At small distances, you're a little rough. Your roughness is growing and growing with one power law, and then it decides, nah, I'm going to grow less fast. This is an experiment with little beads, and they had 3 different bead sizes, and the place that it bent was different each time, but boy, they otherwise look similar. They're measuring the crack roughness by taking the height at one place, subtracting the height at another place, and squaring it. And that height fluctuation grows with distance. All right? So zeta is sort of how fractal your local crack is, and 2 zeta because you take a square, and so the power law for each of these 2 universality classes is r to the 2 zeta. And then the experimentalists, the first set of experimentalists knew that there were 2 theories. One of them predicted a power law about like this one. Another one predicted a power like that one. And so they said this is now the crack at short length scales is being defined by this power law, and at long length scales is defined by that power law. And one of them is the Larkin theory, and the other one is the depinning theory, and so there's 2 different zetas, zeta Larkin and zeta depinning. Now, how do I do a renormalization group not for Larkin alone or depinning alone, but for the whole curve? Okay, so I should warn people, this is yet another example where you can get the wrong power law if you do an experiment in the crossover region. It'll sure look like you have this power law, and then you have this power law, and then you have that power law. And you'll look up in the literature, and there's an example that won the Nobel Prize of a continuously varying power law, and they'll say, I have another one. This is just a plain old scaling function. So here's the scaling collapse. And you can make all of them look the same if you divide them by the right thing. So the way you understand this is you imagine that you have a function of 2 variables, r and some parameter, say bead size, that takes you from one universality class away from it. So this is a relevant parameter, lambda, is relevant at the Larkin scale. So if you're near the Larkin fixed point, there's a flow that drags you away. And then you have a universal scaling function for the behavior not just at the critical point, but as lambda gets bigger. And then how am I going to pick curly C in order to have it change power laws? Well, I want this number, when r is small, to give this. That just says curly C goes to a constant as r is 0. as R over this crossover. This is like a crossover R star, a crossover length. So below the crossover length, this is small, and so the scaling function is constant. Then you get the Larkin prediction. And then what do I need to make this, to make it go as R to the depinning? Well, I just make x, I make it go as x to the 2 times zeta depinning minus zeta Larkin, plug that in, I get the zeta depinning. And that's just what this is doing. Is everyone good? So this is crossover scaling. And Friday we will talk about a jamming, an analysis for jamming that Xiaoming Mao, Danilo Liarte was the first author, Xiaoming Mao is second or third, Olaf, last name? Stenum was who's not speaking here, so I don't have to remember his name. And Tom Lubensky. They did the original calculation, and we're going to improve on it in various ways, and mostly make it explainable to a real audience like us. Okay? That'll be Friday, and we can stop now.
Any other question?
The scalings, the several kinds of scalings you have discussed here today and yesterday, these are for finite temperature critical points or for zero temperature critical points?
Many of the systems that I described, maybe all of them, were zero temperature avalanche-like problems. But all of these phenomena, crossover scaling, singular correction to scaling, dangerous irrelevant variables, also happen at finite temperatures for plain old ordinary thermodynamic transitions. They happen in models of economics, I don't know, everything. Yeah.
I was just wondering if we can say that this is can be applied for both quantum critical points and
quantum critical. Oh, crossover scaling is a big deal in quantum critical points. That's in fact my usual example. I don't want to give it here because we're studying disordered elastic materials and not quantum critical points. But yes.
Okay, thank you.
It's the best example of crossover scaling. Coolest, not the easiest, but the coolest, yeah.
Okay, so any other questions? Do not forget that you take a photo now, so outside, before going to have lunch. Thanks, Jim, for this very nice talk.
Thank you.